Welcome to The Explainer. Today, we're going to talk about something you rely on every single second, but probably never even see. It's the hidden workhorse of our entire electrical world, the humble but absolutely essential electrical transformer.
I mean, really think about that for a second. Power gets generated at some plant, maybe hundreds of miles away from you right now. And somehow it travels all that way and arrives perfectly, ready to charge your phone. How does that even work?
Well, here's the catch. To send electricity over those huge distances without losing a ton of energy, you have to use incredibly high voltage. We're talking thousands and thousands of volts. But if that raw power hit your laptop or your phone charger, poof, that'd be toast, instantly. So you've got this massive gap that somehow needs to be bridged.
Right, so this tension between the super high voltage needed for travel and the low voltage we need for our stuff, that is the grid's great challenge. And solving it required a pretty brilliant and elegant solution.
And this is it, the transformer. Now, static device is just a fancy way of saying it has no moving parts to wear out or break down. Its one magnificent job is to take electrical energy and change the voltage, either cranking it way, way up or bringing it way, way down, all without messing with the frequency of the current.
So how does this magic box actually pull it off? It's not magic, of course. It's just a really, really clever piece of physics. Let's peel back the layers and see what's going on inside. At its heart, a transformer is beautifully simple. First, you've got an iron core. Think of this as the perfect road for a magnetic field to travel on. Then you wrap two separate coils of wire around it. You've got the primary winding, where the electricity comes in, and the secondary winding, where the new transformed power goes out.
Now, the secret sauce that makes this whole thing work is a principle called Faraday's law of induction. It sounds complicated, but the idea is amazing. As electricity flows into that first coil, it creates a constantly changing magnetic field in the iron core. This invisible pulsating field then induces a totally new electrical current in the second coil. And the wildest part? The two wires never even touch.
And this incredibly elegant principle, this induction, it lets the transformer perform two very distinct but equally important tricks.
It can be a step-up transformer, which takes voltage and jacks it way up, which also lowers the current. That's the key for sending power over long distances, because lower current means you lose way less energy as heat. Then, on the other end, you need a step-down transformer to do the exact opposite. It takes that dangerously high voltage and brings it down to a safe, usable level for our homes and gadgets. So how does it know how much to change the voltage? This is the best part. It's not some complex calculation. It is brilliantly simple. It's all about the number of times you wrap the wire around the core. The ratio of turns in the first coil to the second coil directly sets the voltage change. If your second coil has half the number of turns, you get half the voltage. It is that predictable and that precise.
Okay, so now that we've got all the pieces, we can follow the entire journey, from that massive power plant all the way to the phone in your pocket.
And here is the true genius of this thing, the part that's just mind-boggling. Because there are no moving parts, almost no energy is wasted. The big power transformers are up to 99% efficient. Just think about that. Nearly all the power that goes in comes right back out. It's a truly stunning feat of engineering.
And because of that incredible efficiency and versatility, you start to realize transformers are literally everywhere. They're the giant gray cylinders you see in power substations, some of them weighing hundreds of tons. And they're also the little black boxes plugged into your wall for your phone and your laptop. They're hidden inside heavy industrial machinery. They're used in sensitive measuring tools. They're just the silent, unsung heroes of our entire electrical world.
So this simple, static box, a piece of technology that's been largely unchanged for over 100 years, is what makes our modern life possible. Which kind of leaves you with a big question, right? As our energy needs change, as we move towards renewables and smarter grids, what does the future hold for this quiet, essential marvel? What will its next great leap be?